So now I just want to go over some terminology surrounding the notion of derivatives. So the first one is I would like to talk about the verb differentiate. Differentiate is a verb that means find the derivative of. You can imagine this being a command on, let's say, a future quiz. We might see the quiz might say differentiate x to the fifth, and what that means is find the derivative of the function f of x equals x to the fifth. It's tempting to say that the word must be derive, like say find like derive x to the fifth. That sounds appealing, but it's wrong. It's not the correct usage. You'll see it on the internet, and you can generally tell that materials that use that term were prepared by calculus students rather than by calculus teachers, who would always use the term differentiate. The next word is an adjective, and that is differentiable. That's how it's pronounced. And it's an adjective describing a function that has a derivative. The reason that's a useful word is that not all functions have a derivative everywhere, and we're going to see that in a minute. We're going to see an example of a function that does not have a derivative everywhere. The way we would describe that is we would say that the point is a point where the function is non-differentiable. So, the example usage of that term is a question that might say find all points where the function f of x equals absolute value of x is not differentiable. That's the correct usage of that word. So finally, the last term is a noun, and this is the noun differentiability. So this is the quality of being differentiable. An example usage of that would be the statement differentiability implies continuity. I'll get to in a minute what that means, but I'll give you an example of it rather. But what that means is that if a function is differentiable at a point A, then it is also continuous at the point A. If it's not continuous at the point A, it cannot be differentiable at that point. It's possible for a function to be continuous at a point but not differentiable. So it's not that they always go together. What I'm just saying is that you can't have continuity, you can't have differentiability without also having at least continuity. So that's, sorry, so um, you can think of these terms differentiable and differentiability in the same vein that you think of the words continuous and continuity. Continuous is a description of a particular function at a point. So is differentiable. We talk about a function being differentiable at a particular point. Differentiability is the quality of being differentiable. So the same way that continuity is the quality of being continuous. They're both nouns. They relate to their adjectival forms. So let me turn now to an example, but before we even do the example, I want to show you some examples of what graphs look like of points where a function is not differentiable. So first of all, we may have a corner. So a corner is something that looks like this. In other words, where the function actually turns a very sharp corner. This is an example of where a function is not differentiable. Another one that looks a little bit like a corner is called a cusp. You should be getting the idea that functions are not differentiable where they're not smooth, where they make a very sharp turn. We would say that they're not differentiable. Unfortunately, that's not the end of the, and by the way, I'll show you why that is in just a second, but um, yeah, unfortunately, that's not really the end of the story. There's another situation, two more situations actually, where a function is not differentiable. And by the way, these are all pictures where the function is not differentiable at some point A. It's differentiable everywhere else in the picture, just not at A. So it's not, just like with continuity, we don't say function is continuous or it's not. We talk about where it's not continuous or where it is continuous. Just the same, this function with two lines that meet at a corner, it's certainly continuous there at B, and it's certainly continuous there at C. It's just not continuous at the corner. No, not continuous. It's certainly differentiable at B. It's certainly differentiable at C. It's just not differentiable at A. And it is continuous at A, by the way. It's just not differentiable there. Let's look at the third example. This is a vertical tangent. In this case, since we know that the derivative gives the slope of the tangent line, it makes sense to say that a vertical line which has no slope, it has an undefined slope, does not have a derivative. So when the tangent line, when the slope of a curve appears to be completely vertical at a point, we would say that the derivative does not exist at that point. The function is non-differentiable at that point. And finally, when a function is not continuous, we would say that when a function is not continuous, we say that the derivative doesn't exist there either. That's what I mean when I say differentiability implies continuity. If the function is differentiable, then it has to be continuous. So if it's not continuous, we know it can't be differentiable. So those are some graphical examples of a function being not differentiable. What I want to do now is do an example in which we ask the question, is a particular function differentiable at x equals 0? And I'm going to show you why this function is not. So recall that the derivative of f at 0, f prime of 0, is equal to the limit as h approaches 0 of f of x plus h minus f of x over h, which in this case is equal to the limit as h approaches 0 of the absolute value. Oh, sorry, not x. I want to put in 0 here because we're doing it at a specific point. So f of 0 plus h minus f of 0 over h. So this is going to be 0 plus h minus 0 over h. Now, simplify that a little bit more, we get just the limit as h approaches 0 of h minus 0 over h, which simplifies to the limit as h approaches 0 of absolute h over h. Now, in order to evaluate this limit, what we need to do is, since we have an absolute value, and we know that absolute value is defined differently depending on whether we're to the right or left of its vertex, we're going to have to treat this in two cases. We're going to have to look at what's going on to the right and what's going on to the left. So what I want to do is evaluate this from the left and from the right to see if I get the same answer. So first let's do the right. Let's do the limit as h approaches 0 plus of absolute h over h. Well, for positive values of h, the absolute value of h is just going to be equal to h. So this can be the limit as h approaches 0 plus of h over h. Those cancel, giving us the limit as h approaches 0 plus of just the constant 1, which equals 1. Just clear it, that's 1. Now let's do the left side. The limit as h approaches 0 minus of absolute h over h is equal to, for negative values of h, absolute h is equal to negative h. Remember this, that absolute x is equal to x for x greater than or equal to 0 and negative x for x less than or equal to 0. There's a reason I emphasized that because I knew I was going to be doing this example. So this is now equal to the limit as h approaches 0 minus of negative h over h, which for the same reason above just equals the limit as h approaches 0 minus of negative 1, which equals negative 1. Well, look at this. We get 1 and negative 1 depending on which side we approach from. So since this expression was defined as the two-sided limit, and we just discovered that the one-sided limits are not equal to each other, we now know that the two-sided limit does not exist. That means the derivative doesn't exist. So we would say that f prime of 0 does not exist. So we can say that, we can say that f of x is not differentiable at x equals 0. So you were waiting for an excuse to use that big word differentiable in a sentence. There you go. This is a correct sentence using the word, having done some actual math to support the use of that sentence. So there we go. Just want to make this whole thing fit on the page. Now, okay, so why does this make sense? Why does it make sense to say that this absolute value function is not differentiable? Let's take a look at the absolute value function. I just want to draw it in a different color. So there's the absolute value function. Now imagine that you're an ant crawling along here. And let's suppose that you're no longer interested in what y value you're going to end up on, but you're interested in how steep the slope of the function is. If you're an ant crawling along on the positive side of the x-axis, you're going to say, it looks like the line I'm crawling on has a constant slope of about 1. But if you're the ant's friend walking along on the negative side, you're going to say, no, you're wrong. You're going to have, it looks like a slope of negative 1. And you're never going to be able to resolve this up to the point. Depending on which side you approach from, you're going to conclude that the slope of this function is simply different. And you're never going to resolve that when you get to that corner. That's the significance of the corner and why it shows there's no tangent line. I realize many people would like to say, well, let's just split the difference, just like King Solomon, and say, well, the average of these looks like it's about a flat line, so let's call that the tangent. But no, that's not how we do things. We don't just split the difference. We say that if we can't decide that it's one or the other, then it's simply not resolvable, and there is no derivative because there's no slope of the tangent line. Now you might say, how is this any different from the situation like this, like a parabola, where we know that the slope of the tangent line at the bottom it looks like it's horizontal? And it is. The reason is that if the ant was crawling down here, he might say, yeah, these are two cousin ants, I guess. And the one on the right is saying it looks like this is a very steep positive slope. And the one on the left is saying it looks like that's a very steep negative slope. But the thing is that as you get closer to here, see how for both of them it flattens out and they both go to each other. They call each other on their little ant cell phones and say, "Ah, now I get it. My slope is getting shallower and so is yours. So even though we're coming at it from different directions, we both seem to be getting to a slope of zero." For the ants on this triangular function with the corner, they never get to that realization. They both come crashing into the point zero, each convinced that they're right. This one is convinced that the slope is positive one. This one is convinced the slope is negative one. So there's never this kind of motion toward an agreement, and that's why we would say that this very smooth function here still has a derivative at x equals zero, but this one that turns a very sharp corner does not.